Welcome to lesson number 5, composition of functions. Up to this point, you've been looking at operations of functions. And so either working with the quotient of functions, the product of functions, the sum of two functions, or the difference of two functions. Now what we're going to be looking at here is working with functions within functions. All right, so in order to kind of understand what this means, let's look at the first few examples here. When a pebble is dropped in a pool of water, ripples in the shape of circles form on the surface of the water. So if I have a pool of water right here, and if I drop a pebble into the middle here, what is going to happen is I'm going to have ripples that are going to form and expand outwards. The radius of the outer ripple is given by the formula r, or radius, is equal to 0.3 times t, where t is the measurement of time, where r is the radius in meters, and t is the time in seconds after the pebble hits the water. If the area of the circle is a is equal to pi r squared, combine this formula with the radius formula for the outer ripple to write a formula for the area of the circular ripple. So we're looking for the area of these ripples after each second. All right, so in order to find that, we know that the formula for the radius of the outer ripple, so if we're looking at this ripple, the formula for that is r is equal to 0.3t. And we also know that the area of the circle is a is equal to pi r squared, just a standard area formula. Now if we combine this, if we know that radius is equal to 0.3t, then we could combine that with our formula for area, which means that the area for the circular ripple after a certain amount of time is going to area, if we add this 0.3t into our equation here, is going to be 0.3 t squared. And we could expand this, and when we do that, we're going to be left with pi times 0.09 t squared. All right, so what we did was we combined two functions. We combined the function of the radius and the area. All right, so let's look at a couple more examples. So this one is about a Toyota Camry, a 3.5 liter V6 2012 Toyota Camry. We're told that it has a fuel efficiency of approximately 8.2 liters per 100 kilometers. And the cost to fill it up, the cost of gasoline, is $1.25 per liter. So the volume in liters of fuel used can be written as a function of the distance, and distance is in kilometers. Complete the following for liters in terms of distance. Okay, so if I know that I'm going 8.2, if I'm a fuel efficiency of 8.2 liters per 100 kilometers, that's going to tell me as a function of distance, I'm going to be left with 0.082 d. Okay, so that's my fuel efficiency, or the amount of liters I use per distance, in terms of my distance used, which was 100 kilometers. So all I did was I divided 8.2 liters by 100 kilometers. Next, the cost of C dollars of gasoline used can be written as a function of liters. Now complete the following for cost in terms of liters. Well, we know that I'm going to spend $1.25 per liter, and so that is a function of my cost in terms of liters, so that's 1.25 L. We can find the cost of gasoline in terms of the distance traveled by combining these two functions. So what we're going to do is combine this function and this function. If we substitute the formula for the first function into the formula for the second function, we can write cost, so the amount it takes to actually fill up my car, as a function of distance. Now in order to do that, I know that I have 1.25 liters, which is equal to the cost. But I also know that liters is actually equal, as it told me up here, liters is equal to, as a function of distance, 0.082 d. And that's what I'm trying to do. I'm trying to figure out the cost as a function of distance. And so if liters is equal to 0.082d, then I can do what we did up top by substituting my value of r into my area equation. So what this is going to become is 1.25. Remember, L is equal to 0.082 d. And so as a function of distance, my cost associated is going to be 0.1025 d. All right, 0.1025 d. Okay, so what we did there was we combined the two functions, and when we do that, the new function is a composition of the first two. And so this is what we have when we have composition of functions. Now, this next example, they want us to look at the function h of x is equal to 2x plus 3. Now, when we have h of x, this function can be thought of as being composed of two functions, just like we did here, right? This was a composition of my distance and my volume, and they both were associated with the cost down here. And so with this function h of x, we could say that it's a composition of two functions. So the first function is we were multiplying x by 2x, and then this would be the function that we would say is f of x. And then the second function that we have represented here is we're adding 3 to that value of x, and this is denoted by function g, and so we would say g of x. Now, the composed function h, right, h of x says first multiply x by 2 and then add 3. And what we use here is an arrow diagram, and these arrow diagrams are just going to help explain what is going on here. Okay, so don't be overwhelmed when you see this at first. In fact, I'm going to cover part of it up. Okay, so if I look at my first function of f, remember what we were doing first was we were multiplying by 2. So if I start with the value of x, I'm going to multiply by 2, and my second function, g of x, tells me that I then add 3. Okay, so I first multiply by 2, and then I add 3. And my function h of x ends up being 2x plus 3. And so if I look at the zeros here, if I have an x value of 0, and I input it into my equation here by plugging 0 in for x, 2 times 0 is going to be 0. And then if I add 3, 2x plus 3, my answer for h of x is going to be 3. Now if I add my value of 1 in for x, 1 times 2 is 2. If I add 3, I'll have 5. And so that's all we're doing for our values, and that's going to tell us how my function h of x came to be. Okay, so when h of x, what's going on up here? Yeah, so when h of x is written as g of f of x, note that the function f is applied first and the function g is applied second. So this is important. Now let's look up above here again. So the function h of x, remember that we looked at on the last page, was equal to 2x plus 3. And we were told that it's a composition of two functions. First of all, function f of x, which was equal to 2x, and then g of x, which was equal to x plus 3. Now the composite function h of x can be written in the form h of x, or it's equal to g of f of x. Okay, so h of x is equal to g of f of x, and when you read something like this, we read it as g of f of x. Or another way we can write it is g of f of x. Now, this is important. when we write the h of x as a function g of f of x, note that when we're actually breaking it down and using our arrow diagrams, what we want to do is apply the function f first. And so if it was the other way around, if it was f of g of x, then we would add 3 first and then we would multiply by 2. But if f is on the inside, that is the function that is applied first, and the function outside the bracket is applied second. Now what this means is h is going to be referred to as a function of a function. And yeah, this is useful when you do calculus in the future. Now let's consider the composite function h of x is equal to x squared minus 2. Now describe in words two operations in order which can be applied to x to end up with x squared minus 2. Okay, so if we're looking at this function h of x, the first function we're going to do is going to be square. So that's the first operation that we apply to the function. So the first operation is square, and then the second is to subtract 2. The second operation is subtract 2. Now we want to complete the diagram, the arrow diagram, and write h of x as a composition of the two functions, f and g, where this function h of x is equal to g of f of x. And so here I have f of x within my brackets, and so that means I'm going to start with that one first. And if I'm starting with that one first, I know that if I look at my original, or if I look at my composite function, I'm going to be starting with x squared. So if I have a value of x, I'm going to square it. And then secondly, for my second operation, which is g of x, I'm going to subtract 2. So x squared minus 2. So this tells me that my first function, f of x, is going to be equal to f, or x squared. And if g of x squared is the second operation here, then that means that I was going x squared minus 2. And so remember that x squared was function f of x, but my g of x is going to be equal to not x squared minus 2, but x minus 2. Now, same thing down here. Different function. We're looking at h of x is equal to x plus 4 cubed. First thing I'm going to do is describe in words two operations in order which can be applied to x to end up with x plus 4 cubed. Now the first operation we're going to do is add 4 to our x. Okay, so first add 4, and then second we're going to cube. So the second operation is cube. So we're going to do the same thing we did up top, complete the diagram and write h of x as a composition of the two functions f and g. So remember, first thing we did was we added 4. So function f was to add 4, which means that if we have x, we're going to add 4 to that, which means that f of x is equal to x plus 4. Now, function g of f of x, remember f of x was x plus 4. And what we did here was we cubed, right? The first thing we did was added 4, and now what we're going to do is cube. And so we're going to be left with, once we cube, we'll have x plus 4 cubed, which tells us that the function of, and well, I should do that there as well. But that tells us what the function of g of x is. The function of g of x, since f of x was x plus 4, g of x is just going to be x cubed. All right, and so that is the composite function of h of x. Now let's do another example. Hopefully you're starting to get the hang of this. This is pretty tricky, so if you are not understanding yet, don't worry, don't be too alarmed, because this is probably, yeah, this is difficult stuff. Now consider two functions. Now we're kind of working the other way around. Now we're combining two functions. Before, we were taking a function h of x, which was already a composite function, and then we were breaking it into its two functions. But now we're given two functions and we need to combine them. All right, so consider the two functions. F of x is equal to 3f(x) and g of x is equal to x minus 5. Now complete the diagram to determine a formula for the composite function h of x is equal to g of f of x. So remember, if f of x is on the inside, we're going to start with that one. And so we were multiplying it by 3. We're multiplying our value of x by 3, which would leave us with 3x. And so if f of x fits in right here, then that's g of f of x. And the second function was to subtract 5 from this. So that's going to be 3x minus 5. All right, so 3x, and then we're subtracting 5 from our function of f of x. So if I have g of f of x, this is going to be left, what I'm going to be left with is 3x minus 5 for h of x. Now we want to use a similar technique to determine the formula for the composite function k of x is equal to f of g of x. Now you see what happened here. Before, when we were working with h of x, that was equal to g of f of x. But now we're working with f of g of x, so we're gonna switch it around a little bit. So when we were working with f of x up here, remember that we started with function f. But now what we want to do is start with function g. So we're going to be left with x, and put my arrow there. And instead of f on top here, we're actually going to have g. And function g of x tells us that we start by subtracting 5. So subtract 5. And when we do that, we're left with x minus 5. Now what we do is function f. Now function f told us what we had to do was multiply by 3x. So multiply by 3. And so if we multiply x minus 5 times 3, what we're going to be left with is 3 times x minus 5. And if we write this out, this is k of x is equal to f of g of x. And in this case, remember that we're starting with g of x, and so that's going to be function f of g of x, and g of x was to subtract 5, x minus 5, and function f was to multiply by 3, so we're left with 3x minus 5. Now we could leave it like this, or we could expand that to give us 3x minus 15. And this is actually a better answer, so I would go with this one here. Okay, so I'm going to break this video into two parts. I'm going to finish this page, but then after that, I'm going to have another video that you will watch for part of the class on Friday. And, well, you'll watch it on Thursday night and then do it on Friday. But I'm going to run through this first. Now, composition of functions. This is kind of just an overview of what we just did. So consider the function g of f of x. Remember, you can read this as g of f of x, where f of x and g of x are given. And use so if you are given f of x and g of x, then this is the procedure you're going to use to determine g of f of x, or remember, we can also say that that's h of x. Okay, so start with your function g of f of x. And then what you're going to do, if f of x is in the brackets, you're going to replace f of x with the formula for f. And so up top here, the formula for f was 3x. And so we replaced that with 3x. And then what we do is apply the formula for g. And in the above example, it was x minus 5. And then we write the answer in the simplest form. Okay, so let's look at this example. Given f of x is equal to 10x plus 1 and g of x is equal to 2x minus 5, we want to solve to determine g of f of x or g of f of x or h of x. Remember, this can be written in a number of ways. So let's start with g of x. G of f of x, sorry. And so, good, g of f of x. Now what we want to do is replace f of x with the formula for f. And so I'm going to bring this g down, but I'm going to replace f of x with the formula for f. And my formula for f is 10x plus 1. 10x plus 1. Okay, good. Now, what I want to do is apply the formula for g. Now, the formula for g was 2x minus 5. And so if I apply the formula for g, this 10x plus 1, that will take the place of x in my equation for g. And so what this is going to end up being is 2x, which is 10x plus 1, minus 5. And then what we want to do is write the answer in simplest form. So that means we'll have to expand this. 2 times 10x is going to give me 20x. 2 times 1 is going to give me 2. Minus 5. 2 minus 5 will give me negative 3. So we're going to 20x minus 3. And this would be my expanded equation. Okay, so one more example, and then yeah, we will do the second part of this video next class. So if f of x is equal to 2x squared minus 1 and g of x is equal to 3x minus 4, find g of f of x. And remember, g of f of x is equal to g of f of x, or h of x. Okay, so the first thing we're going to do, actually I should line up my equal signs here. So first thing I'm going to do, remember, is replace f of x with the formula for f. Okay, so the formula for x and f in this case is 2x squared minus 1. And the next thing I need to do is apply the formula for g to this. Now g was 3x minus 4. This takes my place of x, 2x squared minus 1 minus 4. If we expand this, we're going to be left with 6x squared minus 3 minus 4, or 6x squared minus 7. Let's do this example here, g of x. Okay, so what this looks like, I don't know, you're like, what the heck? G of x. So we start with my function, in this case, by replacing g of x with the formula for g of x. And we'll have to do that twice, right? So 3x minus 4 in brackets. Next, I'm going to replace that with the function g of x again. So that's 3 times my value of x, which is 3x minus 4, minus 4. And we're going to get 9x minus 12 minus 4, which is equal to 9x minus 16. Okay, so I know this may seem daunting at first, but just practice this stuff, ask questions, and you'll be able to do it.